Okay, now we're going to skip ahead to section 8.1, and again we're going to think about what's happening here. We're going to look at where we've been. We've done descriptive statistics, where we talked about the mean, the standard deviation, a proportion, and we started into inferential statistics where we estimated a population proportion. And now we're going to talk about testing the hypothesis, or testing hypotheses. And that's just a claim about a population parameter. Just like when you learned your first science class, you talked about what a hypothesis is. And a hypothesis is a claim or a statement about a population. It's your best guess. So in the last lecture we talked about chicken pox, and we had a previous study that said 95% of adults have had chicken pox. That's a claim. And so we can test, is that true or is it not? Do we have evidence to support that statement or don't we? Now, one of the things that I'm going to remind you of is statistics can't prove anything is true or anything is false. What statistics does, it gives us evidence against a statement, or it fails to give evidence against a statement. And we'll talk a little bit more about that as we go forward. So what we're going to do in this section is we're going to talk about hypothesis tests in general. And then in 8.2 we're going to talk about hypothesis tests specifically for a proportion. This is also known as a test of significance, and we have a standard procedure for testing that claim. So what we're going to do is we're going to start with a population proportion. We're also going to talk about a population mean in the next section, and then in the last part for this unit we'll talk about standard deviation. So here's some examples. A company that claims that their method allows couples to increase the probability of having a baby girl. We can test that using data from a sample. So we can make assumptions about a population parameter from sample statistics. We can also look that this newspaper says that this company claims that a majority have heard of Kindle as an ebook reader. We can test that. We can test, is 98.6 degrees actually the mean body temperature from a population that we choose, and we carefully design a sample. We must consider the context of the data and the sampling method. We have to have good samples before we can make good inference. So what we're going to do in this section, we're going to talk about the null and the alternative hypotheses. We're going to talk about test statistics. Before we had such easy access to technology, we found critical values, which were the borders, the limits. If it was beyond the critical value, we had strong evidence. If it didn't get to the critical value, we didn't have strong evidence. But what we're going to be doing mostly is we're going to be talking about the probability, which is the p-value. So we're going to calculate a test statistic, and because we have easy access to technology, we can find the p-value, the probability that we would get that value if our statement is true, and then we can make conclusions. But here's the biggest part. We want to state the conclusion in simple terms that anybody can understand. And this is in your book 360, and it's a wonderful way to remember what do we do. And so what's going to happen is we're going to go down this list. We are mostly going to find the p-value. If we were doing the critical value method, we would find this using the tables, but guess what? We might talk about it, but because we're going so fast in this course, I think I'm just going to leave it because I don't want to confuse you. There it is on page 360 for your reference. Now there are some flowcharts in that barrel fold table, and those might help you as we go forward. We're going to deal with the rare event rule. So that means that when we look at the p-value of something happening, if that probability is very, very small, if our assumption is true, then our assumption is probably not correct. Okay? So just here's a hypothetical assumption. I think dogs have 3 legs. So I'm going to go out and I am going to find a sample of dogs, a simple random sample, and I'm going to find what proportion have 3 legs. And when I find the proportion of dogs in my sample that have 3 legs, and I find the probability that if all dogs have 3 legs, my statement is true, that probability is going to be very, very small. If it's smaller than my alpha level, then I can throw out that assumption. So that's what we're doing, is we're looking for evidence against a statement. And so this summarizes steps 1, 2, and 3. So first of all, we set our parameter equal, and equal is very important to some claimed value. This is called our null hypothesis, and it's h sub 0. And what it says is there is no difference. It's a statement of equality. Now, statisticians sometimes call this Ho. And so we're going to test that null hypothesis directly, and then we either reject or we fail to reject our null hypothesis. And that is the statement that we use in our hypothesis testing. Now our alternative hypothesis is sometimes H sub A. Your book calls it H1. And so it's a statement of what we think might be true. Sometimes people call our alternative hypothesis as Ha. Our alternative hypothesis is always a statement of inequality. We might be testing if something is just not equal, is less than, or is greater than. But we never use greater than or equal to, less than or equal to, because there's no equal anywhere in our alternative hypothesis. So again, we're going to identify our claim. We're going to put it into symbolic form, and we're going to have our null hypothesis is always equal to some value, and our alternative hypothesis says that it's not that value. It's either greater than, less than, or not equal to. So here is an example. And I know you can read this, but we have 1,009 consumers were asked if they were comfortable with drone deliveries, and 54% said no. Our sample proportion. And here's the deal. It says is not comfortable with drone deliveries, and our statement is that the majority. So when we talk about majority, we are talking about more than half. Now, look at that statement. That's our claim. Which kind of hypothesis is that? So I hope as you were thinking about this, that you said that is our alternative hypothesis because it doesn't have an equal sign in it. So we're going to think about this, and we're going to look at how many do we need to have to be significantly high, and is our result of, so here we go, 506 is just a little bit more than 50%. That's not very far from 50%. But if we got 1,006 out of 1,009 who said they didn't like it, then that would be significantly high. But what about our results? So let's go on. So we needed to identify the claim, and the claim is, in words, is the majority is uncomfortable with drone delivery. And we're going to put that in symbolic form as P is greater than 0.05. Now, in our hypotheses, we always use the parameter. We always use the parameter. So we're going to use P, not P hat, in our hypotheses. So then if P is greater than 0.05 is our alternative, then P, and I'm going to change this to P is equal to, that's an equal to, 0.05 must be true. So we're going to look at that, and then we're going to set up our alpha level. So again, we make our alpha very small if the consequences of rejecting a true null hypothesis are extreme, and we use 0.05 and 0.01. They're very, very common. If you aren't given an alpha level, feel free to assume it's 0.05. Okay. And this slide says the same thing that the last one did. So here we go. And these are the test statistics that we're going to be dealing with. And in this subsection of the subunit, we're going to be dealing with the proportion. So we are testing P. In the next subsection, we're going to look at means, and we have two tests that we use, and we'll talk about that when we talk about 8.3. And then in the third subunit, we're going to talk about standard deviation or variance. And here are the formulas for our test statistics. We'll talk about where those come from, but there they are. They're also in a table in your book on page 362. So in step 6, we're going to calculate our test statistic. And this is the value that we use in making our decision about our null hypothesis. We take our sample statistic and we change it to a z-score or a t-score. And don't worry about a t-score right now. We'll talk about that more when we talk about means. But we always make the assumption that our null hypothesis is true unless we find evidence against it. So again, here's our test statistic for a proportion. And you can see this looks pretty familiar. We used p hat q hat divided by n when we found our margin of error in our confidence intervals. But we're going to use p from our assumed value from the population, and then Q would be 1 minus P. So we're going to find the difference between our sample statistic and our population parameter divided by an estimate of the standard deviation. And we're going to use z-scores in when we test for proportions. And so I tried to dim this in that we're not going to talk about this right now. So here we go. We're talking about the drones, and our claim is P is greater than 0.5, and we need to test to see if our number of, basically this is the number of our successes and this is the number of our failures, and it comes out to be okay, so we can go on. And so we want to find the test statistic. And so in this case, when we do p hat, our test statistic is going to be a z, and you know all about z's and the standard normal table. So here we go. So when we do this, we calculate our p hat, which is our successes divided by the number in our sample. We are going to do this, and we get a z-score of 2.54. Okay, ponder that for a minute and think about the standard normal table, and where would that z-score be? Now, if we did a critical region, what we would do is we would find a z-score that beyond that would be our alpha. And if our score gets out here in our rejection region, then we can reject the null hypothesis. And so we have different kinds of tests. When we use a not equal to, we have a two-tailed test. We're looking for alpha divided in both of the tails, like we did with a confidence interval. When we're looking at a less than alternative hypothesis, then we're looking for the area down here in the left tail. When we're using a greater than in our alternative hypothesis, we're looking for the area up here in our upper tail. Now, the p-value method means that we're looking for a p-value if the null hypothesis is true. What is the probability that we would get a value from our sample as extreme as we did? So we know our z is 2.55. It's a normal distribution. It was a right-tailed test. And so we looked at technology, and we are looking at the p-value, and they tell it is 0.005, and let's show you where we find that. We're going to set our alpha, and we can find the critical value, which I'm going to say don't worry about that. We want to take it to the p-value. So this is what we want to do because we want to use our technology. If we have a small p-value, that is strong evidence against our null hypothesis. So that is far away from what we'd expect if our null hypothesis is true. It wouldn't happen very often. Now, a large p-value says, it's going to happen quite often if our null hypothesis is true, and that fails to give us evidence against the null hypothesis, so we can't throw it out. So again, we're not going to worry about our technology. I mean, how to do it before technology. If you want to do that, it's explained in the book, and for this unit, you use table A2, and your p-value is less than alpha. That is the one that we are going to concentrate on. If we did this before technology, we would compare the absolute value of our z-statistic with our critical z, and when we're doing means, it might be a t-statistic. Don't worry about that right now. And here is a flow chart, a really great flow chart that in your book is on page 364. It's unfortunate that we use p's for everything. When we talk about p-value, that's probability. When we talk about a lowercase p, that is our population proportion. And I think I mentioned someplace that some textbooks use a pi for the population proportion to help you keep it separated from p-value. So here we go. When we have a two-tailed test, then alpha is divided equally between the two tails of the critical region. And so when we take our z-score test statistic to our standard normal curve, if it's close to the mean of the distribution, then we fail to reject. If it's out here in the tails, either the high tail or the low tail, then we can reject it. When we have a less than, our alpha is in the left tail. So remember, our sign points toward the tail we're interested in. And so if our test statistic lands in this blue area, we don't have any evidence against our null hypothesis. If it lands down here in this rejection region, then we have evidence against it and we're going to reject it. So here's our drone delivery, and they have set up a rejection region. So when we set our alpha as 0.05, well, when we need 0.05 area above, then we know the critical value is 1.645. But our sample z-score came out to 2.55. It's way up here. So it is in the rejection region. So that tells us we can actually reject the null hypothesis. When we have an alternative hypothesis that points to the right, then we're looking, our rejection region will be in the right. So again, you can reject your null hypothesis when your calculated z-statistic is greater than your critical z-statistic. Now, if you're doing a two-tailed test, you could do a critical a confidence interval, and if your null hypothesis is outside the confidence interval, then you can reject it. And so we can either reject or fail to reject, and that is our phrasing. And so if the p is low, the null must go and we reject it. If our p-value is greater than alpha, we fail to reject it. And then our last step is always to restate our decision. And so we should never say reject, fail to reject, never. And so here is a good statement. There is sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone deliveries. Oh, you don't have the flowchart in your textbook, but you have a really nice table on page 366 that give you some examples of how you start your claim. So in your conclusion, never say, I reject the null hypothesis or I fail to reject the null hypothesis. Use things like, there is sufficient evidence to support the claim. There's not sufficient evidence to support the claim. This study suggests that. And then go on and either state your alternative hypothesis or your null hypothesis. For me, you're never going to use the word except. Some texts do. We can't prove anything with statistics. We can only show that something is false. So when we don't have evidence against the null hypothesis, we say fail to reject. So let's talk about type 1 and type 2 errors. A type 1 error is mistakenly rejecting the null hypothesis when it's true. And we set that when we set alpha. So alpha is the probability of a type 1 error. So when we set alpha as 0.05, we are setting the probability of a type 1 error at 5%. A type 2 error is the mistake of failing to reject the null hypothesis when we should. And we use the symbol beta to represent a type 2 error. Now, if you are looking in your book, they go into power and all kinds of things that deal with beta. We're not going to worry about that too much. So here's the deal. So if we think of the hypothesis testing in terms of a smoke detector. Now it tends to go off every time you burn something in the kitchen. That's a type 1 error. So it's alarm without a fire. But a type 2 error is a fire without an alarm. Think about which one is worse. Well, a type 2 error is going to be worse. Now how do we avoid a type 1 error? We just take out the battery. But when we make the type 1 error bigger, that also increases the size of the type 2 errors, or it increases the probability of a type 2 error. So when we reduce the chances of a type 2 error by making the alarm hypersensitive, that can increase the number of false alarms, which is a type 1 error. When we have no fire and no alarm, it's good. If we have no fire but we have an alarm, that's type 1. If we have a fire and no alarm, that's type 2. If we have a fire and have alarm, that's no error. So when we talk about the null hypothesis, that's like no fire. Where null hypothesis is true and we don't reject it, that's good. But if we reject it when it's actually true, that's type 1. If the alternative hypothesis is true and we don't reject the null hypothesis, then we have made a type 2 error. If the alternative hypothesis is true and we reject the null hypothesis, then again there's no error. And here is another table that talks about type 1 and type 2 errors. And that is in your book on page 368. And so again, when we talk about type 1 error, that is our alpha. An increase in sample size causes the type 2 error to go down. When we decrease alpha, we will cause an increase in our type 2 error, and the other way, if we increase alpha, we'll cause a decrease in our type 2 error. And so when we increase the sample size, we decrease both type 1 and type 2 errors. So it's always best to err on the side of the bigger sample. Now power is simply 1 minus the probability of making a type 2 error. specifically testing a claim about a proportion. So let's go on to 8.2. We're going to do the normal approximation method. So here's the important stuff. N is the number of trials. P hat is the number of successes divided by the number of trials. We know P is the population proportion, and that's always found in the null hypothesis. So it's whatever number is in that null hypothesis. And then Q is the complement to P. And so again, we need to have a simple random sample. We need to have conditions for binomial distribution, that there's a fixed number of samples, there's only two outcomes, and that the probability doesn't change. And then we need to have the number of failures and the number of successes are both more than 5. And here is the formula for our test statistic. Now, most of the time we are going to use p-values using StatCrunch. And again, p-value is not proportion, is not the population proportion. We'll always use, I try to use a capital P for p-value, and it will always say p-value. So I would recommend that you use StatCrunch. So let's look at this. There's our formula, and we get the p-values automatically from StatCrunch, and you can look in your book how to do it with critical values. So when we're talking about proportions, a confidence interval method is not equivalent to the p-value method, because we're estimating the standard deviation when we are using the confidence interval. So it's best to use the confidence interval to estimate the population proportion, but when we're testing the claim, we want to use the p-value method. So here we go. We're going back to our drone deliveries. So the number in our sample is 1,009, and 545 said they were not comfortable with having drones deliver their purchases. I'm going to take what one of my instructors called a bird walk. I can just imagine that the drone is coming to bring you something, and you have a neighbor down the street who doesn't like drones flying past their house, and they go outside with their rifle and they shoot the drone down. Okay, let's birdwalk back to the problem. We want to test the claim, and we're going to test the claim that most consumers are uncomfortable with drone deliveries. And whenever we talk about most, we're going to mean more than half, greater than 0.5. And there is our alternative hypothesis right there. So check the requirements. It's random, 2 categories, 5. So we're good to go. So let's look at this, and this is from the TI-8384. You can do it with that. Go to YouTube and do a search for z-test of proportions with the TI-8384, and you'll get a video that shows you how to do this. But you can see our z-score is 2.5499. Our probability is 0.005. So if we go back to our list of how do we do this, here we have our claim, the opposite of our original claim, and then here are our hypotheses. And remember, our null hypothesis is always a statement of equality, and then in this case our alternative hypothesis is greater than 0.5. That was our original claim, saying that the majority of people are not comfortable with drone deliveries. We're going to set alpha equals to 0.05, and we need to calculate the p-hat, the sample statistic. So we're going to do that. 545 over 1009. P is our assumed value from the null hypothesis. Q is the opposite of that. We're going to go ahead and do the math, and we come up with 2.55. This is a right-tailed test. Let's go to StatCrunch. Here's a good picture. Here is our test statistic, and we want to see what's the probability that it would be beyond that, and it comes out to be very small. Let's open up StatCrunch. Okay, I'm going to go to Stat, Proportion Statistics, one sample with summary. My number of successes for this was 545. My number of observations was 1009. We want to do a confidence interval, and notice that we already have 0.5 in there for our null hypothesis. Our alternative, we think it's greater than 0.5. Most people are uncomfortable. And then we simply do compute. And there we get the same z statistic, and we get the same p-value. Okay? So keep that in mind as we go forward. Our p-value is less than alpha. So because that's true, we can reject the null hypothesis. And so we can say, and here is our summary, we conclude there is sufficient evidence to support the claim that more than half of consumers are uncomfortable with drone deliveries. Here is an example where we're going to need to find the number of successes. So we get 29.2% of adults have sleepwalked. Of 19,136, what's the actual number? This is a percent problem like you did back in 8th grade. We're going to take 29.2% of 19,136, and we get 55,087 with some decimal number, but we always round it to the nearest whole number. And then again, we can test that significance. And I'm going to let you go through this. All three requirements are satisfied. Here are our hypotheses. We think that fewer than 30% have sleepwalked. We're going to set our significance level. And we're going to do this by StatCrunch. And you can see we get a negative z-score, but our p-value is 0.008. And when we went to StatCrunch, we made sure that our alternative hypothesis was a less than. In StatCrunch, when you put the number in your null hypothesis, the same number populates your alternative. But you need to make sure that the sign between is correct. Okay, think about what a p-value of 0.008 means. So, because 0.008 is less than or equal to the significance level of 0.05, we reject the null hypothesis. So, there is sufficient evidence to support the claim that fewer than 30% of adults have sleepwalked. I would like to see it. This study suggests that fewer than 30% of adults have sleepwalked. So in this section, we have discussed how we come up with the test statistic for claims about a proportion. We looked at the p-value method. We looked at the confidence interval method and we practiced obtaining our p-hat.